probably the easiest one to work with. And then for it, you'll end up with 5 columns. And I guess 1, 2, 3, I'll just keep that. So C11, C12, C13, C15. And then this would be, this is just like a schematic of it. But this would be, this would say treatment 2 is on, this one says treatment 3 is on. So the Y's are stacked, and actually they are. If you look at the data set, the Y's are stacked. The first batch is in treatment 1, the second batch is in treatment 2, and the third batch is in treatment 3. So that'll be fine. Okay, we don't have to change that. Okay. And so how do you get these 2 columns in Minitab? Actually, there's a command that does it. It's just in the so the Minitab. So far, this would be Minitab, right? Getting this in, and then here's Minitab starting up again. I'll just do INDI C3. And then it's going to make the indicator 1 with all zeros too. I'll just throw that away. So it's going to make, I have 3 levels in C3, okay? It's going to make 3 columns. The first one I'll just throw away. And then I want C11 and C12. And that'll make those columns. All packages have something like this, so you can put a design matrix together. Although I don't know if SPSS does this. Really sass. Okay, so now I created those 2 columns. You can print them out and make sure that it's got them. And then this is all the X. That's just C2, so I can just copy C2 and C13. So now I have those. Okay. Now, if we look at this design we've got so far, that is the reduced model design that the slopes are all the same, right? So there's only one slope parameter in that problem. And that's on column 13. You know, this would be beta 1, beta 2, the intercept would be beta 0, beta 3. And that's my reduced model for all slopes the same. That's the homogeneous model. But I want to fit the full model, so I want the C14 and C15. And those are just increments in slope. And you can get them very easy. All you have to do is multiply C11 and C13. We just won't do all that. That'll create this, right? If you multiply these 2 columns together, and there's your increment in slope, right? Slope for the first level, well, okay, let's do the last one. So that's going to be this. Now, the biggest thing in this is to know what that thing means, all right? And you can do it, you can come across, take an observation and like the last one. What's the expected value going to be? It's going to be 0 times beta 1, right? We have beta naught. The intercept, this will be 0. Go to beta 2. We'll have beta 3. We won't have beta 4. We'll have beta 5. So I claim that the expected value of a y3, say y3, okay, group 3, will be, we'll have the intercept, we'll have beta 2, we'll have beta 3 times x, and we'll have beta 5 times x. So that's the model. This is the model for an element in group 3. Likewise, how about a y2? That'll be treatment 2. You'll have an intercept. Intercept's always in. You'll have the intercept will be in. Beta 1 will be in. Beta 3 will be in. And beta 4. So its linear model is beta naught plus beta 1. Plus beta 3 plus beta 3 times. And then finally, how about a y1? Well, the intercept is in, and beta 3 is in. Okay, so are there any questions on that? See, you have 3 different models. If you're in y3, then this is your intercept, right? And this is your slope. If you're in y2, this is your intercept, it's different. It's beta 1, not beta 2. And this is your slope, it's different. It's beta 4, not beta 5. And of course, if you're in the first level, then this is your model, this is your intercept, and this is your slope. Okay, so that would be the incremental model, and that's how you would set up a Minitab. It's set now, okay? With these 4 commands, you have that model. You can make that design matrix. You're in control, all right? You're in control when you make the design matrix. You know exactly what you're fit. Okay. Now you'd probably want to do some plots too. You could break these things apart at the bottom. Yeah. Remember how we subset things in Minitab. Do a subset. I haven't done it for a while. You can do a copy. You used to be able to do a copy and use rows. I think there's 10 elements in each, so you could, if you just want to do like a plot on the first one, but this is, I have the checklist. I would copy. All I need is that. Just have to copy something. It's also, you can click on editing, and it will talk about how to do that. So that way you could do the plots, right? I need to do that for the Y's too. You can just make them all. And then plot what C22 versus C23. So you could do plots. You might, how else could you do plots in Minitab? With this, the original data. Actually, it's not bad, right, because you have the indicator. You can probably, if you look at plot, if you open up plot with the click, and you see a thing with a few lines, or it might even say groups, the next thing to click on, and you can plot Y versus X, and you click on C3 as your group, and then it'll give you 3 lines. Hopefully it'll give you scatter plot, 3 different plotting symbols. Probably you can add any square space. These are all across. See, they really project each other. So, but getting back to our analysis of covariance, then the first thing we want to do is we want to plot we want to test what? We want to see H naught will be homogeneous slopes. In terms of symbols, if you just turn off beta 4 and beta 5, we'll have it. Right? So this is in our full model fit would be this, right? You might want to do residual plots anyway. So there's my full model, right? Minitab, well, it's R. And then the reduced model is what? The reduced model is constrained by H naught. That's an easy one. That's just columns C11, C12, right? C11, C12, C13. C11. So that's just and then you want to get the minimum dispersion here. I think it comes out in Minitab. This will be D full, right? You can get solid hazard too. And here you'll get D red. And then this will be the test. Okay. So there it is with Minitab. Any questions on that? So you can do the analysis of Minitab, it's not that hard. Okay. You could also look at the R. So let's do it with R. With R, we'll fit the full model, and then we'll fit the reduced model. There is a in cell X, which will give you that design for this. But you could just piece it together too. So it's just piece it. I'll just get all of it. rotate lines and,
Are we supposed to be seeing something? Have you switched over to the computer?
oh, yeah, right.
And it's
Okay, I just got into R and then, I loaded library R fit and then, I'm bringing in a data. Okay. So now the data is in. Then last time we went over the routines, the wrappers that will do the analysis, right? Here I just want to do it by scratch the way we just did it, so maybe you have an understanding of what's going on. So I got it in my Y. Let's pick off Y. That's the first column. So there's my response, right? There should be 30 values there. And then this call X code, that's, I think that's the second column. Right? So there's my covariate. And then let's call in third column. But let's use the same numbers that I did in Minitab. I need a C11, and we could just build it. You can build it with, it's a cell X function. I'll show it to you later. Let's just build them, okay, with what we have, and I don't have to use that. So my C11 will be what? About 10 zeros, right? Those not transposed. So there's my C11, right? That's going to be second treatment, right? Then I need C12. And I could actually back up and just fix this one, right? And you can see the mistake I made. I didn't rename it, so now that's that. That's the same mistake I made last time. But you would find it out. In fact, you would get it. So now I have 11 and 12. Here's my covariate, right? So that's 13. And then I need 14. And then finally I need 15. Or you could just call it XMAT for the design metrics. And I'll just combine those columns, right? There's my design. Any questions on that? No, we just built it by scratch. Now I know exactly what I'm fitting. Okay. And then I can do the two things.
Can you show the original data set up there too, just to see how it changed?
This was the original. I didn't overwrite any names, so I'm okay. Then I can just do this. You could just use that smack, you don't have to use the C's if you want. So you can just say why I wiggle one. And then here's the reduce. And then reduce is, see how easy it is to subset norm. I just want all the rows, but I only want the first three columns, right? Or I could have built it too. Then you have to know, and I think it's this, right? We did this yesterday. It's just called the full, right? It's just this, right? So it's $2. I don't think the function is. Right, and then B red will be what red is. So there's a full model just for example. So you drop by 14 points. That seems very hard, long, high, right? Thickness. You just need to tell that. And you want it off the full model fit. So that's going to be very hard. It's called that W for Wilcox, and it's just it's full divide by 2, right? 2 constraints. And divide that by tau added 2. So it's 18, and you can get the p-value. The p-value would be 1 minus the probability of an f at fw, right? And then you have 2, and it's in your design you have an intercept 2, so you actually have 6 parameters to fit. So you use a degree of freedom for each parameter to fit. So it's 30 minus 6.
I have a question. What is the TAUS hat that's part of the?
Oh, that's the scale parameter used, which we've never used. We haven't had these. You're going to do a confidence interval for the intercept. Although you can, and that's figured in the standard errors that come up. Parameters in the full model. And you have to include the intercept. So there's 5 columns that we talked about, and there's the intercept, so 6. So 30 minus 6. So it's highly significant, right? 2 values, 0 to 4 places. Any questions on that? if you plot these lines, they're really cross. We could substitute plot it. Why don't we do at least two of them? I just want to guess this one. So this is one. Okay, so then I want xy1 would be what? It would just be xy. And I just want the rows with I and D equal to points. And then xy2 and then x1, I want the rows with n equal to. So you have to have a double equal. So I could do the plots now. Well, let's just plot on one plot. We just use different things, right? In one instance. So you always have to start off right on a plot. It's like you have to make the big screen. So you have to be careful. One way to make the big screen is just plot everything. So it's x, y, I want just the x's. And the y is right. I don't want to see. Just punch white space. I'm not going to worry. So there's my big screen, okay. Why do you have to do this? Because if you plot x1 and y1 first, and the biggest y1 was 10, but the biggest, overall the biggest y1 was 20, you would never see it because it would stop at 10. Actually, it stops at 16. Yeah, we can just plot together. So you just want to, let's just do points. Because the x is on the road. This is going to be tedious. Let me just use 1. It's actually talking about the numbers. So there's the first treatment. It's almost flat, right? It's like quadratic to me. I think we'll have a little problem with it again. Now, I keep on careful and do something stupid. There's a crossover. Very two, you might be fine. You could see that from, well, I don't know. Two's going out this way. There's more of them going out. It's probably, they're both different. You can see it on the increments too, if you did summary. These are two slopes. They're much different than one. This is the increment over level 1. Right? Now we did an overall test. You know, if you really worried about alpha here and you did it with t-ratios, you would have to cut alpha by 2 and do a bond for running, right? Although it'd still be highly significant. You cut these by 2. But we just did an overall test. We didn't have to do that. In fact, if we did protected LSD, we did an overall test, and we could come back and say, hey, these two differ from the first. Now, do they differ from each other? Probably. You can go through this. The easiest way is just to rechange the design. So I'm not worried about that today. That's something you might want to do. Okay, questions on this one? On this one, what, if you wanted to do another analysis, you would select it and go back to the plot. Just it's after the fact. Well, but you said there was a difference. You might select certain points, like maybe you're interested in the first quartile of the x's somewhere down here. And then there's definitely a difference between 1 and 2. Here you're doing an extrapolation on 3 of them. There's no 3's in this area. So you should be very careful. If you did it around here, at least you have all the data, from all levels. But I don't think you're going to see much difference. Well, maybe. I haven't got to it. But that's what you would do. You would select points.
I have a question on the output. Not the plot. On the output it says reduction in dispersion test. Is that the F value of the?
That's all beta is equal to 0 except the intercept. It's equivalent to this thing here. It's just this restandard.
Okay. So it's not the F value of.
Yeah, it's d of 0 minus d of 4.
Okay.
Divided by 6. Divided by time 2.
So it is the F. All right. The big F.
Okay, any other questions on it? Okay, then our last talk on we got what, like we have about 2 lectures left. Go through landmark block designs. And if I have time, we'll do the ordered alternatives by thinking. We start talking about it too. Often you have more than one factor of interest, and then you set up a design where you cross the factors. You do what's called a cross design. So now you have 2 factors, A and B, and this is at A levels, and this is at B. But the design is crossed. It's A cross B, or you would write this in plus B2. Okay? And as I was saying last time, this was a big step in design. We had to convince people to use this design. We used to just do one after another. But this design is just full of lots of information. Okay, so then you can gather the data from just the cells, right? So this would be the Jth level of B, right? This would be the ith level of A. So here's your cell ij. And you should put the model in here, right, and everything else. But you can think of storing the data in here too. So the data are going to come in at cross, right? They used to do designs like this where they would just, they would fix B and then just change A one at a time. Okay, and then they would fix A and then change B. So actually, after they've done, A plus B experiments, that's all they have is that column. And they missed all this information. Okay, but that's not what we're doing. We're just doing this cross design. And, each of these cells are like the experimental units. An experimental unit is in the cell. So you have to set the level for A, set the level for B, and then you take the observation. And you shouldn't do them in order. It should be completely randomized. Sometimes it's very hard to do. Sometimes you have natural things where you can set this up as a huge field. And A could be the fertilizer and B could be the amount of water. You can really control those two for each cell. And the cell is, the design is actually that. One place where stats really helped is agriculture. You go to a school which is mag school, you often see a very good applied stat department. There's a lot of interaction between the ag people and the statisticians. Because in ag, you can do these experiments, right? You don't have to worry about people. You don't have any ethical things to worry about. Of course, what they do with the soil, that's another story. Okay, so then you would just model the data this way. Right? This would be the kth observation. And the ith level of A. And jth level of B. And then, here's the one way design. You could use mean and median, it won't matter because we're taking the contrast. Our things are good for contrast. So that would be your model, and then we'll call this the full model. There's no structure. Okay. It's the reduced models where you put the structure in. And the best structure of all is additive structure. The cell is uij, but the only thing that makes it different is this is what I have. So level I is in, but it's the difference between that and the overall mean, okay? So in that first parentheses, there's no J's. Right? And in the second parentheses, there's no I's. So you're just looking at the difference in the ith level, the mean in the ith level of the overall. And then back to this, this would be u bar I. And then you're saying I can describe uij with those two parameters. It's all in the margins. That's what you're really doing. Nothing else. It's just the grand mean. You just centered things. So you've just centered things. This is just a function of the margins. And this is a great model because there's a hypothesis, there's two hypotheses in here. This model had nothing to do with I. These are all zero. And if that's true, then I is not on the right-hand side. Okay? And that says factor A might have some effect, but it's an overall effect. And it's the same for each level of B. There's no A effect. Okay? It could be an overall one, who cares? It didn't make any difference which level you used. It doesn't matter how much water you used. Okay? It doesn't matter what detergent you used. It doesn't matter whether you go to a Ferrari or an Acura. The effects are all the same. And then the other one would just be, these are all normal. The alternative is not the normal. It's the same thing on factor B. So this would be no B. No separate B. Maybe in a car thing, it's you're running on different gasolines, different octanes. Maybe it doesn't matter what octane you use. It doesn't affect the speed. It doesn't matter what fertilizer you use. The one we'll look at is we'll look at a couple examples. And the one will be lifetime of a motor. Maybe we start talking about that. And there's two factors: installation and then temperature. We can test the motor maybe from Mars. So you really have a variety of temperatures. There's the emission, and you take that would be your factor A. Different brands of motor, and B would be temperature, and then you're going to see how long it lasts. Okay. Now this is great, and there's one thing you can do with these. You can perform these plots. So these are called profile plots. I'll put an R function back where it is. We should have it in the package to do this. But anyways, your profile plots, you want to plot averages. And so, okay, so you set out to do this with I equal to 1. Okay, and suppose you have this additive model. And then from j equal 1 to j equal 2, you have the same increment no matter what I is. Well, what that translates down to is you end up with a parallel profile. So if you plot for I equal 1, the mean, as you go from block 1, level 1 of B to level 2, for I equal 2, you might start up higher, but you go the same slope. The increment has to be the same, okay, because it's directed by that. So wherever this goes, and you end up with these parallel profiles. And that says it doesn't matter where you are in level B, the difference remains the same. So you do these profile plots, and then if they're parallel, it indicates okay. Well, this is a great model. You can, these are called main effect hypotheses. Okay, if you reject, if you retain H naught A, then you don't have to worry about different numbers. If you retain H naught B, then you don't have to worry about different numbers. So that and B are nice hypotheses. Now, this doesn't have to happen on you. I could do these profile plots. I'm just going to use the sum of means. I'm not going to use this structure to do the plot, so it's a non-parametric plot. And they don't have to be. You can do a plot like this. So do something that's not parallel. So then, what's that? Well, it's what's left. You have this full model, and the additive model didn't catch it. Okay? So what's left is called inner. And then you can just work this out, it comes out to this. And these are called interaction parameters. It's the residual of the additive model. If the additive model is okay, then the gamma ij should be close to 0. Okay, and then that's what you want to test. And it's usually called A times B. So then this becomes like your ANOVA table, and on the third line, you have the one you don't want. Yeah. And the degrees of freedom, if you go back, it's a constraint because they're all centered. And then in a two-way analysis, this is the first hypothesis you have to test. And if you reject this, then there's interaction in it, and you probably shouldn't test these. All right, you get into a lot of discussion with people. Schematic. Here's a 2 by 3, right? And then you can have, see the average, as long as the average is the same. See the average here would be 0. You just have to make another average 0, which is not parallel at all. So this would be minus 8 plus 5 plus 3. See, and if you're just in the margins, you just see 0. Right? The average is 0. There's no effect for A here. It's the same. The average effect is the same. There's a disaster in the middle. They're all different. And it definitely matters what row you're in. So this would definitely be an interaction. You have to row across here. So if you have interaction, people will argue, why do you want to test for main effects? And some people test anyways, they test like an average main effect. But you can have situations like this, okay? H naught A is true, but there's definitely interaction. So you have to be careful. Okay? So that's, so how do we do this? Well, we have a which just called RA over B, which will be form this task. So this one I don't think I'm going to do by scratch. I just want to talk a little bit about it, do some examples. So let's look at a couple examples. And go ahead and okay, I have let's see, let's do, I think it's back. Okay, we built this wrapper so it looks like this is exactly what you would do in R and function would be doing. You just don't have this. So in this case, this would be the response, and this would be the first factor, this would be the second factor, and then this would test the interaction. The only thing that's different is you have to put the data in the data. So let's look at the data. is real data. So it's a 3x3 factorial design. It's in Nelson, so actually Jerry might put this on the page. But y is log of the lifetime of the motor installation, I. So there's 3 installations, and then there's 3 temperatures. Okay, and this was the original data. And it was best if we just took the logs. And this is the log version of the data. So it's making these big numbers fairly small. It's very skewed if we cut those in. So we can do it. Okay, so then we just, I don't think I need that. I have it. I brought that in. Must be, let's put this around. So here comes the data. And we just talk about the data. So this is our response to cell line. The logs to data. We can do a histogram of it. So it's not residuals, you have to be careful. You can do a histogram of the original data. Anyways, we looked at some plots and we decided that we just do them. Okay. And then we talked about, I think we talked about data frames. You have to make things factors. That's all it does. Data frame, you just bring in, this is our response. And then insulation is, I called it, this is the insulation, and this is the temperature. I should have something just next to it. It's there, it's inside, right? Anyways, here's the here's your node. So this is your interaction between the two factors, insulation and temperature, and it's very significant. And if you run a least squares analysis on this, it will come out to be nice. But if you do that cell mean plot, which I should do, but maybe it's a very function to do it. We can look at the here's the cell means. Not the means, this is the location estimates from the wireless. I don't know if you can see. So 7.3. I think these come out in order. So 7.3, 8.0. I'm very close. I mean, I probably need 2-digit accuracy. 6.5, 7.3, 7.3.
Write it down.
5.5. 5.5, 5.9, 5.6.
Isn't 5.5 wrong then?
Pardon me?
5.5, isn't that wrong?
Yes, 7.3. I don't know if you'll be able to see the cross or not. You just plot those verses 1, 2, 3. So 5 to 8. It's 5.5. 5.7. 5.6. Connect these, this would be A1. This would be B. And then A2 would be 6.6. 7.9. That's I'm doing upside down.
Yeah. Thank you.
A1 would be 7.2. 8.11. Yes, they're not. I think if you plot them the other way you just have to plot these. I think it's more of a cross. You should plot both of them, all right? So what you want to do is plot
Do it first.
no, I know I made this mistake. So you want to make sure I keep going that way. Let's start at 7.3. So 7.3, 6.6. 5. And then B2 would be 8. So see, they're not parallel. This way you can see that. The other one's 8.1, 7.1, yeah, these ones. And then 5.7. There it goes. This is an interesting example because least squares didn't project. So in the papers we wrote, we had to have that plot. And these are the robust fit, okay, with the cell means and, but if you do the least squares fit, the same thing happens. Okay, well, one sign is the Let's look at a very famous data set, it's called the Box-Cox data. Now, 48 animals were exposed to 4 treatments and 3 poisons. It's not good news. The response is a survival time. I think they were dogs. But this is a famous Box-Cox data, and this data really has some outliers in it. And when you do the profile plot, I'll try to find it. But when you do these profile plots, they're really cross, and whether it was outliers in the action. I can talk a little bit about that. So I want to finish this. We'll go over this example next time. And, then we'll definitely talk about a randomized block design because we'll get back to some traditional non-parametric agreement tests, which you go over agreement tests. And for that, I have a rank-based version, but it's, I don't think I'm going to go into it in this class. It's another, we don't call it R, we call it JR. So we should talk about the randomized block design. And then if we have time, we'll talk about the alternatives, these strong groups. Okay, so we're getting down, and the final will be like a week from Tuesday. There'll be no more quizzes. Okay? Quizzes are over. Not going to have no homework. I know you're sad about that. And I think I'll talk more about this next week, but I think the final will be
Could be what?
multiple choice. So when we finish the final, we can all leave. Go. Well, actually, we'll talk more about it next week. Okay, so we're almost done. We want to go to the randomized block design. What are alternatives?